Disseminate, a computer science research podcast, the DuckDB in Research series.
Hey folks, and welcome to the DuckDB in Research series. This is the show that explores all the wonderful ways DuckDB has been used in the world of research and academia. That might be as a vehicle to teach databases or as a platform to experiment and to develop cool new things. So yeah, if you're a researcher, an engineer, or just a general database enthusiast, then this is definitely the show for you. In today's episode, I'm really delighted to say that I'm joined by Paul Gross, a PhD student at CWI in Amsterdam. I'm not going to attempt the Dutch pronunciation of what the acronym actually means, but yeah, maybe you can, Paul, explain it for you. I've tried before and I always get it wrong. So, but yeah, Paul is here to talk about some of the research that he published earlier this year at the Conference on Innovative Data Systems Research, also known as CIDR. No, it's not a beer festival, unfortunately. But yeah, cool. Paul's research focuses on this research, should I say, looked at factorized aggregations and worst case optimal joins. So first of all, welcome to the show, Paul.
Yeah, thank you very much for having me.
Cool. Well, let's dive straight in and give us the sales. Tell the listener kind of what they've got themselves in for the next sort of 30-40 minutes or so. So yeah, give us the sales pitch for. I didn't actually say what the title of your paper's called, so maybe I should do that now. That'd be a good idea, right? So yeah, your paper's called Adaptive Factorization Using Linear Change Hash Tables. So yeah, what's the TLDR on this? How would you explain it to your grandma? Take it away, Paul.
Yeah, so the paper Adaptive Factorization is basically on allowing you to reduce the intermediate size of your query. Basically, most of the analytical queries, you don't really have a million rows in your output, because at the end the output is designed for a human or maybe now for LLM, and they can't really understand that. But usually the intermediate contains millions of rows, and with factorization or with adaptive factorization, you can basically avoid those big intermediate results by only processing on like a reduced set of data. And the cool thing really is for our paper that you can basically use 90% of the things that are already in a normal analytical database system to do that. And you don't really need a new big operator for that, but you can basically integrate it quite easily. And also to add, like, this was joint work with my supervisor at the time, Daniel Tenwalde. And I think you already had him on the show as well on DuckPGQ.
Yeah, he was on in the first season on DuckPGQ. So if you're interested in this, listener, you should definitely go check out Daniel's show as well. It's really good. So that's cool. So basically, the aim of the game here is then we have these really big intermediate. We can often get these really big intermediate sets of things while we're doing our queries. We want to make those as small as possible, right? Or not kind of end up with this sort of state space explosion during our query processing. Cool. So yeah, my grandma definitely gets it now. She knows. She understands. Cool. So yeah, there was also another thing that I kind of maybe mentioned at the top of the show. I mentioned the phrase worst case optimal join. Maybe we can talk a little bit more about what that actually means, because it always I see that acronym, I see what that means. It always scares me a little bit. So maybe we can kind of talk about what that is a little bit as well for the listener.
Yeah, it still scares me a little bit as well. But basically, the idea, I think the most common example is like a triangle query. And for example, you have a social network where you have friends relationships. So friends meaning user A is a friend of user B, and then user A is again a friend of user C. And then like everybody has like 10 or 15 or 100 friends, I don't know. And the idea is basically, okay, and now I want to have a triangle. So like whose friends relationships form a triangle. And in a normal query plan, usually what you do, you have binary join plans. So in a binary join plan, you would join the relations to like relation at a time. So first you would get, for all the users, get all of their friends. So you would have this explosion of friends, because now if everybody has 10 friends, then you will get 10 friends for everybody, and then like you end up with 100 tuples per user. So you have this explosion, and it's quadratic. And then with the second join, you will create like this filtering join, because like now you only want, you have those two conditions. You want to have, like, if you have friend A, then friend B, and then you want to have friend C. C has to be a friend of B and A now to close the triangle. So this is a very filtering join. So then you exactly have this explosion of the intermediate result, like you first join will return a huge intermediate, and then the second join will filter that again. And what you do with worst case optimal joins basically is you go tuple at a time, or like attribute at a time. So you will basically simultaneously check all the free relations and then intersect those tuples instead of like doing a relation at a time and having this huge intermediate.
Nice, cool. Yeah, that's a very good explanation. I was just thinking as you were sort of going through it, and you're talking about the social network example about, if you've got this amount of friends, then it can be problematic because then 10 times it's quadratic and 10 times it quickly explodes. I was thinking, well,
Yeah.
I think my social media accounts wouldn't be in any danger of troubling them, because I think like 1 follower, 2 follower, and maybe not as sort of as challenging to the query engine as other maybe, yeah. But yeah, that's cool. Yeah, so that's a really nice description there of what worst case optimal joins are. So yeah, we've got worst case optimal joins and factorization. So why is it taken so long for these sort of techniques to become like adopted in mainstream systems, or what makes them difficult to sort of implement in database systems?
Yeah, I mean, like maybe quick for factorization is basically a method of avoiding those intermediate results. So what you get if you like basically this binary join is a join hash table, like a hash join, and this is actually quite simple. Like you have your build side, you just build a hash table on your right hand relation, and then you probe this hash table with your left hand relation. And let's say you have 10 friends again, so you would have this hash table that has maybe like just a collision chain, and then for each of those two, for each friend you're probing into this hash table, you would get 10 results because like you have 10 hits. So the idea is now to, instead of flattening that and having like user 0, user 1, user 0, user 2, user 0, user 3, you basically have a list of users for this very first user. So like you have user 1, user 0, and then you have times, and then you have this list, user 1, user 2, user 3, user 4, and etc. So, and this really helps because you need less memory, because you don't have to repeat user 0 again. And also, for example, if you want to make like a count aggregate on top of that, then you can use this factorized representation to easily compute the count, because you don't have to expand the whole intermediate, but you can just make like the sum of the length of the lists, because now it's 10. So this is basically the idea of factorization, and this is a very, very useful trick. But the problem is really to handle those lists, and because you have a vectorized execution engine, usually for us, for what we did in DuckDB, and then you don't have one user and then its list, but you have 2048 users, because that's the vector size. So you're always processing those 2048 elements at a time. And then for each, you have these lists, and suddenly your lists are variable length sized. So it's also not easy to provide the memory for that easily, because like one user, maybe like me, has like 2 followers, and then you have Elon Musk in the next, and he has like millions. I don't know how many friends.
Yeah, probably millions. Yeah, if not billions. Yeah.
So this is really a problem, because like having like this variable sized data is just hard to deal with. So this is mainly like, how do you create those lists? How do you make your operators emit those lists? And because like first, like you have to have them, then you have to calculate on them. This is really the challenge. And there like have been several approaches to that. For example, GraphLowDB and Kusu have a very cool way of basically having like a vectorized system, where you basically like you have this first vector, which is the left side of the factor, and then you have the right hand big flat buffer, and then you can basically switch certain IDX. It's very hard to explain without pictures, but there's a very great thesis that I wanted to highlight from Amin on GraphLowDB, so like the predecessor of Kusu. So this is, I think, a good read. Yeah, and
Nice. Yeah. Sorry, continue. Oh, yeah.
yeah, and it's basically, this is like the main reason. Like, how do you make your operators integrate those representations, and then how you execute on them. And this is like for factorization and for worst case optimal join. It's like also two problems. Like these operators are super complex to integrate because they have this complete new way of working. Or I mean, in some sense, they are also simpler, but they are just different in their style. Let's say it like very researchy. And then you also have to decide whether you want to use this worst case optimal join or whether you want to continue with a binary join plan, because this triangle query, it's of course the perfect example, but how often do you run this query on like an OLAP system? It's like no TPCH, no TPCDS query. I hope this is true. Has such triangle.
Yeah, it is now. You've spoken into truth now, basically, Paul. Yeah, it is. Yeah.
This is very easy to checkable, but TPCH for sure doesn't. So.
Cool. So yeah, you actually you mentioned Kuzu and Umbra. Did you mention Umbra? You mentioned GraphFlow, not Umbra. Sorry.
Yeah.
I mean, actually, on a random aside, I just saw the other day that Kuzu actually the project has been shut down, sadly. So yeah, no more Kuzu, which is a shame.
I'm very curious what happened.
Yeah.
It's a pity.
Yeah. I'm sure it'll come out on some Hacker News thread at some point. What's happened, right? There'll be something cool there. Yeah, it always does. But yeah, so you mentioned that those systems have sort of tried to tackle it and have kind of come up with some neat approaches to taking the idea and actually making it sympathetic to like a vectorized engine and whatnot. But what are the limitations at the moment? Like, where are they falling short in putting those ideas into reality?
I think like the most of the systems that really want to have it, like in the sense of like Kuzu has support for worst case optimal joins. Umbra has it because Umbra is very feature complete. So it's possible definitely, but for us the challenge was also like how to make something that Mark would merge. so how to not touch too much, and there's really the problem. Like how do you and also I mean this is for different systems. Like if you're not like a prime graph database and like you're expecting a lot of cyclic joins or like these kind of things, then it's like then you can have the resources to integrate that. So like it's not unsolved. It's just like complicated in the sense. And then this is like from the implementation part, and then it's still hard to really plan those elements, because you have to have those very certain conditions. Like you want to have this, or like you want to avoid this intermediate result, and sometimes maybe your intermediate result is not actually large. Like maybe your first join, which would be the binary join, is even also selective, or like the third join is not filtering. Like what do you do then? Like you like then your binary join plan was maybe better, and for that you really have to rely at the moment on cardinality estimations and like sketches and like all of these statistics. But it's like planning is also very hard, and then having this other dimension of now you can choose between this worst case optimal join and the binary join plan, which are very fundamentally different. You can't just swap them on runtime. Is adding a challenge that is, I think, like an academic challenge.
Nice, yeah. For the listener, Mark is one of the co-founders, right? So yeah. So yeah, we've got to get it. That's the bar to get it passed. But that's cool. So you went about tackling some of these issues you just outlined there, and you did that with a thing called linear chained hash tables. There we go, second time. Yeah. So walk us through kind of what they are and what their design is and how they go about mitigating some of those things you outlined a second ago about the challenges of these techniques.
Yeah, I think this was like the linear chained hash tables. The idea is from my supervisor, actually, like Peter Bowens is my PhD supervisor. And I think it's a very neat idea and also a very neat strategy, because we basically implemented them before implementing the factorization, because they enable factorization, but they also provide certain other benefits. And so therefore we could also like sneak in infrastructure for our later plans into DuckDB.
Nice, laying the future groundwork. Oh, look at this now. We've managed to implement this. Yeah.
Also
what coincidence. Yeah.
So it's also like a little bit in this direction, but basically
strategic. Yeah.
strategic PRs. Yeah. Basically the idea is to extend the DuckDB hash join a little bit so that we can use the chains of the hash table later for factorization. So basically a hash join, as I already said, it's a very simple design. You basically have this hash table, you build it on your build side, you probe it with the other left-hand side of the join, and then you're done. And then the big question is, of course, how do you design this hash table? And I mean, like there's like this very fundamental data structures thingy where you can do linear probing either to resolve hash collisions, because I mean hash collisions happen because like two keys basically collide on the same slot of your hash table. So how you do deal with that? Like they're like either you can do linear probing, so you say, okay, this bucket is full, so I will just take the next one, and if this one is full, I will take the next one until I find an empty one, basically linear probing. Or you can do chaining, basically having a linked list of elements, and then like populating that linked list. And both have advantages and disadvantages. Linear probing is very cool because you have all the things inlined, but what do you do if you have a string key or a struct as a key? Like you can't inline everything into the hash table. And you also can get very long probing chains. Chaining is also like is easier if you have like those big keys, but you have a linked list, and linked lists are slow to follow, and they can be scattered across memory. Hash chunk can be gigabytes of size, so it's very, very slow to follow those chains. So basically, what we did, it's a little bit involved, but it's also not super hard. Like the other systems do is similar. So basically, if you have if you want to insert a tuple into the hash table, you first need to hash it, and then you want to get the offset from a part of the hash, and then with this offset you go to this slot, and then DuckDB has this chained hash table where for each slot you have this pointer to a chain, and this chain then can have all the different types of keys and like has some memory that it traverses. So the problem now is that you have two types of collisions, basically. Like first is like you have the same key twice in your hash table. For example, if you have multiple, like one user has multiple friends, and like all like this key is then just multiple times in the hash table because it's like the ID of this first user. So then what you have is like the same key collides to the same hash, to the same slot, which is normal. Like you can't avoid that. It's good. And then what you can also have is that you actually have a hash collision. So like you have two distinct IDs you want to insert into your hash table, but the hash just happens to be the same. And it like if you have a small hash table, for example, like 2024 elements, and you want to insert, let's say, 900 elements, so it's so then it's quite likely that those will collide. So, and now because DuckDB has those chains, because the keys, like different keys might go into the same chain, during probing, you always have to walk this chain and say, is this tuple an actual match? Yes or no? Is this the next tuple an actual match? Yes or no? So, and this is kind of slow because you have to do this comparison for every element in the chain. So what we did is basically do some trick to make the linear probing happening with only like parts of the hash. So we add some salt, we call it. So because the pointers in the it's like the the meme. So basically pointers are only 48 bits. So, and our hash table slots are UN64, so we have 64 bits. So there's 16 bits of emptiness, of void, if you're not on Android. And so basically we fill those upper 16 bits with some parts of the hash, and we use this as our tiny key. And on this key, we can then do the inline linear probing. And then we can do linear probing for all the collisions where the keys are actually distinct, and only add an element to a chain if the keys are the same. So therefore, we can guarantee that within a chain, all the keys are the same. So therefore, if we want to probe now this chain with a key, like if we find that the first element in the chain matches, we know that all elements of the chain match. And that we can use to make probing faster. So this is the TLDR kind of thing.
Nice, yeah, that's really cool. So how does this then, so that you kind of, well, the first question I want to ask is that you were saying earlier on in the show that like you wanted to be as least invasive as possible so you can get this PR merge. Did there have to be any significant code changes of actually making, of having this, like, was it easy to implement? Did much need to change on the core product side?
Basically, the salt thingy was already implemented, luckily, for the aggregate hash table, but not for the join hash table. So that was like, it was known as a technology. So that's also good, like, because if you want somebody to maintain it, then like if they saw something already, it's easy to implement. And I think the sort, like also Umbra does something similar, for example. So this is like quite common to do.
Yeah.
And then this, like having those key unique chains was possible in the sense that you already had infrastructure for checking whether the keys match, because you have to do this during probing anyway. So basically it was moving some code also to another part of the build pipeline. And I think it was like maybe like 200 lines of code, like not too much.
Yeah.
And it was like,
Right.
now it's very cool because usually your build side is much smaller than your probe side. So you, like, for each tuple you insert, you maybe probe 20 times. So now, because you do this comparison now 10 times during insertion, you will save it 200 times during probing. So it's like and especially if you have like not that easy to compare keys like strings, it's very beneficial. So that was also the motivation to just add this as a plain data structure.
Nice, cool. So we've got this primitive in there then. How do we go from that to enabling our end goal of worst case optimal joins and factorized query processing?
Yeah, now it's actually quite close already, because now you have those chains and they are key unique. So if you now, instead of like, if you probe your join, and you would flatten those lists, like for each element you would take the first element of the list, emit it, take the second element of the list, emit it. Now, instead of doing that, we just emit a pointer to that chain. So then we basically have factorization. And now if we want to compute a count aggregate on that, under certain conditions, if the group key is also like not within the list, because then we can't really use it. If the group key is in the flat part of the vector, let's say it like that, then we can just again take the sum of length of lists to compute a count. And this is the idea for that. The problem with that, though, is that there's actually, which I realized far into my master thesis, is that there's a much easier way to compute that. Because if you already know that you want to have the count anyway, what you should do is make a group join, which is also like a technology introduced by Munich people. So basically, instead of building the list in the first place, you just compute this aggregate while creating the join hash table, and then you can emit the aggregate directly. So it's a little bit more fancy now with these chains, and then emitting the pointer to the chain, and then only counting the length of the chain, but it's already there. So
Yeah.
that was not very useful.
The, the question I want to ask you, Paul, is where was you when you realized you could do it this other simpler way?
Not at CIDR, luckily.
Okay. In the shower one morning, thought, "Oh my god, I could have done
No.
that. It saved me so much work." But yeah.
I mean, I was talking to people from Munich,
Yeah.
and also with Amin actually, and then there were pointers to that. And there's a paper that came out at the same time which does something very similar, which is, I think, diamond hardened joins from Altan Bierle at Munich, and he also explains that, but only like in a tiny sentence. So, and to be
Yeah,
honest,
easy
I
easy
just
to make.
overread
Yeah.
that sentence.
Yeah.
So
Yeah.
there would have been pointers, but I mean, it's fine. It's fine. It's fine. We learned something, and we showed another way to do it.
Very true, very true.
Maybe not the
Cool.
best.
Yeah, cool. So let's talk about. So you mentioned this earlier, I think, in the show, where you were saying that it's often hard to know when to deploy these techniques based on that. It's not. It's, do you go one way or do you go the other way? It adds another dimension to the complexity already of picking the plan, basically, right?
Yeah.
Of what you actually want to do. So I guess this is where the adaptive decision making comes in a little bit, I think, right? So yeah, and this concept of adaptive factorization. So I guess start off with what's the motivation behind adaptive factorization and what we're trying to achieve here, and then tell us how you went and did it, right? I guess. Yeah.
Yeah, the idea is basically to have those chains of elements. And having this chains of elements it adds some overhead, because suddenly you have this variable length elements you have to kind of keep track of in a vectorized execution engine, which is not trivial. And
Mm.
but also on the other way, you can compute things faster if you don't have to expand them. And to know whether to do this extra efforts of maintaining those chains, it's very important to know whether you actually have those chains.
Mm.
And this basically means, okay, how I need to know that like there are duplicates on the keys of my join side. So which means that will result in those chains. And now if I don't have a special operator for doing worst case optimal joins, but just using the normal DuckDB hash join, then those chains are there for free now, basically, because I would, like in a binary join tree, I would have this first join, and in a worst case optimal join plan that we can now do by not expanding those chains and then using them later in the join plan. We also have these hash table chains. So it's like the first step of the plan is very similar, and by the time where we have to decide whether to now use a worst case optimal plan or this flat binary join plan, we already seen these chains, because we can do this after we build the first hash table. And therefore, you touch the data. You basically don't have to rely on statistics. You can very precisely say, okay, I have like for each value I've got 7 duplicates, which means my chain length on average is 7, which means okay, I can update my cost model with like true values, and I don't have to rely on estimates. And estimating like how many duplicates are there, like there are sketches for that, but they always require like, there are sketches, and what is like maybe, and you only have them usually on your base tables. But what if you're querying a CSV file or a Parquet file, or like another join result? Like you never, like you can't really, like there are cases where you don't have statistics, and then if you have statistics, they are only statistics. They are not like the true value. So that's the motivation behind doing it that way.
Nice, cool. So I guess the next, so I want to ask now about, I want to dig onto the sketches a little bit more. So yeah, from what I'm gathering there is that you don't actually need them, right? Or do we need them? Or how do they fit into your overall approach in collecting these statistics? Like, why do you need them still?
Yeah. So basically, for if we want to do a worst case optimal join like plan now with those factorized elements, then we have to do 2 things. Like first, we have to, it's for triangle query, and it's a little bit hard to explain without a picture, but I will try. Basically, you get these chains, like you join. Let's say we want to make a triangle between like the 3 relations. So first you have to join the first 2 relations, and then because you're emitting those chains, you get for each value of relation 1, you get chains with elements of relation 2. And then you do the same. Basically, this you emit up into your tuple in your pipeline, and then the next join comes, which is also kind of a normal hash join, but then you have like one simple flat condition, which is tuples from relations 1 to relation 3, and then basically you have those 2 lists. And now you can do list intersection. It's it's not very clear, I think, from this explanation, but basically the idea is like, okay, you only have to decide after this first join whether you want to do this or not. And then you can either do worst case optimal join plan or a binary join plan. So now you also, because you have the exact data from the first join, you already know like you have duplicates or not. So you can know whether your things are whether your intermediate is exploding or not. But in order for worst case optimal join to be like really, really performant, or like then you also want to shrink this intermediate again. Let's say like very simple. So how do you know that your second join is actually selective? Or like you don't really have, you only have data on one relation of the 3 relations of the triangle. So now what DuckDB does is also like what every modern analytical system does, is before building actually the hash table for the second join, it first materializes all the data and stores them basically in memory or like splitting to disk in rows. So, and because that, and it does that to then know, okay, how much space do I need for my hash table to allocate this lookup buffer? Because if I have 10 elements in my hash table, then I will make a hash table of size 32, for example. But if I have 1 million, I have to resize this I have to have a big hash table. And it's very expensive to resize a hash table during building. That's why you first want to gather all the data, hash it, and then you know how much data you have to build a hash table on, and then you build this hash table. So this means in this case, we also have a scan over all the data of the second join, and then we can use this scan, and we even have the hashes to populate other sketches to then estimate more statistics basically on how selective will this join be, and so on and so on, and are there duplicates on the second join. And
Nice.
this is basically the motivation for doing it that way. So you have like very exact data on your first relation. You have somehow exact data on the second, and then the third is still an Easter egg. So yeah, it is what it is. Like you can't touch everything.
Nice, cool. I know it wouldn't be 2025 if there wasn't some machine learning in there somewhere, right? So I know you've used some ML as well in sort of, I guess, compared it, I guess, to like normal heuristics and and how machine learning models can also help you decide the various join types you want to do, right? So maybe you can dig into how you applied that and what the trade-offs were and what you found between the two different approaches, the classical versus the modern, I guess.
Yeah, I think like machine learning always, like it sounds like it's a very, very basic machine learning, like a decision tree. So like at the end,
Don't say that. It was complicated. Yeah.
but it's important, I think, to not be like a deep learning model where you don't really know what's happening. I think the machine learning was really more to see whether there's insights above what we would expect.
Okay.
Are there other like patterns in the data that like, because for us it's very clear if like the first join has many duplicates, that means we have an explosion, and therefore worst case optimal joins are probably good. And so the idea is, okay, you have this metric with this feature, which is basically the average chain length of the first join, which is correlated to the duplicates in the first join. And then you have this heuristic. If it's like, I think maybe it's like bigger than 10 or something, then you take this worst case optimal join approach. And then like there's other features where it's not that clear. And so therefore we build also those decision trees to analyze whether there's like more detail to the data. But I think the results, or like the predictability, the true positive rate, it was very similar. Like it was not like the decision tree was outperforming this heuristics just bigger than like average chain length bigger than 10 by 2x. It was very similar, and therefore I would also say like, okay, I would like, if I would implement it, I would use this heuristic because A, like it's simple, I can understand it, and B, it's not that much better. So I think there are places where you can use machine learning in planning, definitely, and there's a lot of work on that. But in this case, I would stay with the heuristics because it's so close.
Yeah, nice, cool. So yeah, that's interesting. It's funny you should say that, because over the years of doing the podcast, quite a few people have had the same sort of opinion. They've been like, yeah, they're good in some very narrow subset of like corner cases of certain
Yeah.
type of workloads, but like most times the juice isn't worth the squeeze, right? It's just stick with something simpler. It's more, you can reason about it easier. And yeah, it's easier to maintain as well, often a lot as well. So yeah, it's interesting that you've also come to the same conclusion.
Yeah.
Sweet. So yeah, the next section of the podcast, I want to talk about some results and evaluation and how well your techniques performed. So yeah, give us some clickbaity results I can like chop up and stick in the promotions for this for the podcast. How did it do?
Yeah, basically, I think benchmarking was not trivial because how do you I mean, you have to have, for us, we mainly focus on those triangle queries because they're the prime example, and you could generalize this to cycles with odd numbers of edges. So because there you really have this explosion. Or like this, like you can do this worst case optimal join like plan very easily. And what we did there is this social network benchmark, and basically we run a triangle query on the schema to get like all the possible triangles you can reasonably get, and then use all of these queries to benchmark whether we want to use worst case optimal join or whether to not, and basically run it once with the normal plan, once with the worst case optimal join plan, and then also recording those statistics. And then we could also say, okay, would our cost model have predicted the correct runner? Therefore, like simulating it. And yeah, it showed that like like always or never using worst case optimal joins was of course inferior to like using some ML or heuristic to decide whether to use it or not. But to be honest, I don't have the exact numbers anymore, like on how much percent or something. But it was worth investing.
Just 1,000,000%. So
Yeah,
yeah,
definitely. I mean,
big
it's
number.
always yeah.
Yeah,
The moment
it
where
was
you
better.
can, the moment where you shape your benchmark, you can always have arbitrary speedups because you can design like your query in a way that it exactly hits your optimization, and then like it's always easy to get arbitrary speedups.
It's easy. Yeah, yeah. Cool. I guess so. This is available. So your techniques now are obviously implemented in DuckDB, so people can benefit from your techniques, right, in your code.
Partly. There's a branch, of course, which is like on my private GitHub, which implements the worst case optimate join, and is also like factories like aggregates on factorization, which I talked about a little bit earlier, where there's actually like the better way of doing the group join, but you can also do it that way. And yeah, this linear probing hash table, it's in DuckDB. I think it's in DuckDB since 1.1 or something. It's quite a while actually, and it has working quite good, I would say. And then I also had a discussion, of course, with the DuckDB maintainers about how we could implement the worst case optimal join, because that like the factorization and the aggregates are solved otherwise easier. And I hope that DuckDB at some point will also integrate that ego aggregation and group joins, but so far not. And unfortunately, it's already have been done. Like research-wise, it's covered, so I can't do it. So it's not a job for me, sadly. I would like to implement it, but I have to focus on newer stuff.
Newer stuff, yeah, more on the cutting edge side of things, right?
Yeah.
Yeah.
Yes.
Yeah,
So
because I was going to ask kind of about whether you have any ways. I guess it's still kind of an open question of how in the wild of like of workloads at large, how often these sort of techniques would be beneficial. So I was kind of getting on the line of, have you had any sort of feedback from people out there in the wild of said, oh yeah, this. Oh, I don't know if any sort of statistics are collected from like kind of workloads that are run and kind
yeah.
of fed back up and like, yeah, we're seeing. Everyone's using worst case optimal joins. Everyone's got a social network as their application, and they just want to do triangle counting constantly. I don't know. Yeah.
Yeah, I think for the default DuckDB workload, which is like on device OLAP, it's not super important. But I mean, there is DuckPGQ, and like the goal is still to implement some of the techniques into DuckPGQ, and like for like as a side note, like DuckPGQ adds like graph query languages to DuckDB, and also some other operators like graph and pathfinding. So it's very very cool and it's also very performant. So then, like because people are using this graph language, you would expect graph workloads. I mean, this is not a crazy assumption, and therefore maybe also like more cycles. So the idea of merging it as an like putting it into an extension is very very cool. The problem is that you probably still have to fiddle a little bit with the hash join. So what do you do? Like, do you copy the whole operator and then replace it, or like it's still like not that easy to implement? But I mean, I really hope that at some point it will end up in DuckPGQ. And
Nice, cool. Yeah, so that's one future direction. Sorry, Paul. One direction you're going to go in with this work next. But is there any other directions? I mean, you teased there. There's some new cool cutting edge research you're doing as well. The new. So is anything else related to this in any way, or is it different?
yeah, I mean, this was my research, my master thesis, and now as a PhD student, I unfortunately, or like maybe also not unfortunately, have a completely different topic, and which is strings and string processing and database systems. So I don't unfortunately have that much time anymore for that. I mean, I'm still doing some join stuff. I try to implement Bloom filter pushdown at the moment in DuckDB. It's also not as easy as I thought it is, but I'm getting
It
there.
never is. It never is.
It's
Right?
never
Yeah.
is.
Yeah.
So, fingers crossed that this is done soon. But now my main research goal is to basically do better string processing in DuckDB, because I mean, strings are a very underestimated data type. There has been a Snowflake survey showing that like I think, or I don't have the number directly, but I think it's like 20% of all string key types are strings. of all join keys or strings. So that's correct. Like there are people using strings as join keys, people using strings to store numbers, to store dates, to store Wikipedia pages. Like there's a lot of stuff in database systems that are text. And now the idea is to basically use compression to first like get it smaller on the storage side, but then also push it through the execution tree as compressed as possible, as long as possible, so that you don't have this huge memory footprint and those like huge chunky bytes in your memory.
Yeah, and their techniques you're going to be implementing in DuckDB as well, right?
That's the goal. Yeah,
That's cool. So yeah, we can do this podcast in again when you finish that and publish that, we can come and talk about some strings as well.
Yeah, that would be a pleasure.
Cool. Yeah, so let's talk about DuckDB some more then, and sort of your experience of working with it and developing and writing code in its code base. So yeah, what would be your overall sort of experience of using DuckDB and like, I guess its extension module, or even just in the code base? Like, what was that like, and what would your advice be to other people who are thinking about getting their dipping their toes in and getting their hands dirty?
Yeah, I mean, I before doing my master thesis, I was more like a front end kind of person, so I did a lot of TypeScript,
Now
and
you've
then
come to the dark side now, yeah.
literally like, so like diving into the DuckDB codebase was quite hard for me in the beginning because like there's like if you don't really have a understanding on on an abstract level of what's happening, like trying to understand it from the code is impossible, I would say, or like maybe not impossible, but impossible for me. So like in the beginning, I really had to look at a lot of Andy Pablo lectures on YouTube to really understand the basics. I think that's the journey of everybody.
Yeah.
But then I think DuckDB is really like readable in a sense. And there's also like one resource which is called, I think, DeepWiki. Yeah, it's DeepWiki. And there basically it's an LLM documentation for the GUT and for open source projects, and DuckDB is in there. And then you can basically ask questions like, how is the DuckDB string storage built up? And it's so convenient because it shows you like what's happening and also shows you like which lines of code you have to look at. So that's really like a nice way to get started with DuckDB if you want to understand something. This is highly recommended. So, and then at some point you start understanding like you have to find like your little spot where your breakpoint hits, and then you're like, yay, I know what's happening, and then you can start changing things and try to meet CICD. Yeah, so it's possible, and then of course it's very nice because it's like running it is super easy because it's on your device, and this means also like developing it is super easy because it's on your device. You don't have to have some Docker in between or like whatever. Like you can just build it in debug on your device, and then you can debug it like every other CLI.
A nice tight feedback loop there.
Yeah.
Which definitely makes development so much nicer when you've got that.
Is. Yeah.
No, that's really cool. Yeah, I guess now I'd like to talk a little bit more about kind of surprises and interesting lessons learned whilst working with DuckDB and with factorization and worst case optimal joins. So has there been any that sort of jumped out when you kind of gone, I really didn't expect that, or that was a bit of a shock?
I think the systems part is always a little bit concerning, and because it's like the moment you touch something, it will touch something else, and then something like you have a different state of the whole thing, and then something like it's always like cascading down to places in the code where you wouldn't expect it to be. And then DuckDB being a production system, meaning that if you want to merge something, like people might want to join on a struct of lists that contains lists that contains structs again, and suddenly you are in very like weird states of the code. So I think for research it's very important to like keep it simple. Like for example, those join thingies, they worked on UN64 join keys, which is probably like 95% of all edge tables in graphs. I hope nobody has string edge tables. I'm not sure.
Somebody will, Paul. Honestly, man. If it's possible, someone will have done it. So
that's true. So yeah. And then like for doing research, I think it's like you don't have to do something production ready. Like that's like two different types of things. You have to show that it works, and then you have to like just say, okay, the CI will keep being read and yelling at you, and there will be 100 tests failing, but it's fine. Like,
Yeah.
so yeah, this is the most like I think I have
Cool,
I'm
yeah.
used to.
I guess it'd be nice to talk now a little bit more about yourself as well, as kind of the man behind the research and all, and so to speak. So, yeah, tell us, how did you end up working? You said you worked you were sort of a front end guy before, and now you sort of worked your way into being a systems person. So, uh, yeah, tell us about that journey and kind of how did you end up where you are?
Yeah, I went through the full stack basically.
So what's going to happen next? You're going to be working on, like, go lower down. You'd be like working on, I don't
Software.
know, semiconductors next, right? So yeah.
Cool, actually. No, I mean, I did my bachelor in Germany, at the University of Applied Science, so that was very like practice focused. I liked it, but I missed always like being at a big university, being at a research university. So I went for my master to Amsterdam, and there, like the first class I had was Peter Bowen's class about data, like what was it, large data engineering or something like that. So, and there I met my two best Amsterdam friends, so also very convenient. They both work at MotherDuck now. And so we all like got hooked by Peter and the lecture, and we went into and then decided to do our master thesis with him at CWI. I think it's Zentrum for Wiskunde und Informatica, but my Dutch is also
I'm glad I didn't attempt it, put it that way, yeah, because that was a lot better than I would have got done with it, so
Fingers
yeah,
crossed that it was
yeah.
correct. It's a very nice place to do your master thesis. Highly recommended. Because I had my own office, or like not my, I shared it with other master students, but it was great to have like a place to go for the thesis and not be alone in the library and nobody cares about you. You like, had meetings with Peter, meetings with Daniel, which were really helpful. So I really, really liked being there. So I asked Peter whether I can stay a little bit longer for 4 years, and he accepted that. And so that's why I'm doing a PhD now. Basically, I just
Brilliant
wanted
stuff.
to stay studying also a little bit. It's a very nice way of work. Yeah.
Yeah, definitely cool. Very nice. So we're nearing the end of the podcast now, Paul. But yeah, before we do finish off, DuckDB recommendation. What's the one plugin extension feature that is your favorite about DuckDB?
I think DuckDB in general is such a nice system being on your device. I think this is very like it's such a simple design choice, kind of, but it makes so much possible because suddenly instead of having a million CSV or Parquet files, suddenly you have them all in one place. And if you want to copy all of your data because you might do something you regret later, you only have to copy one file. You have like joins across different files. You have like all of these very neat features. So it's just since working on DuckDB, like in the beginning, I really had struggled writing SQL. And now all my Python scripts are full of like 10, 15 lines of code, SQL statements doing left anti-joins. And so it's a really, really cool stuff to do. And I think like one recommendation is, of course, DuckPGQ as a very cool extension and like a very nice way of showing what you can do with DuckDB extensions, because the extension ecosystem is something that's very cool to have. And there's a ton of other, like there's also Flock MTL, like it's some AI focus where you can have AI scalar functions
Yeah.
from Amin. And there's of course there's MotherDuck, which is also kind of cool to add like this whole other dimension to DuckDB. So this is I like the ecosystem and the people working on it. So
Yeah. Definitely. I keep trying to get Amin to come on to talk about Flock MTL, but he keeps turning me down. So maybe next time, season 3, I'll get him to come on and tell everyone about it. But it's interesting what you're saying about there about kind of now your like Python scripts are full of these like kind of SQL everywhere. So do you think that sort of time basically spent inside the database and kind of makes you more sympathetic of the way to actually write SQL queries? Is that kind of would be your assessment of it?
I think maybe like it's because I just was forced writing a lot of SQL to write my
Okay.
benchmarks, and then
Yeah.
like it eased my fear of doing that, because it looks
Right.
kind of
Okay.
easy to have those SQL in your Python, but it works so convenient. Like you can like output the DuckDB result to a pandas data frame and then visualize it. It's so cool how they integrated that, and like the querying remote files, like just putting data to S3. It's like, of course, you have those ugly SQL statements. Maybe some people say they're beautiful, but I'm on the other side.
Beauty's in the eye of the beholder, I guess, and we'll leave that one there. Yeah.
But they really take a lot of work away. So that's why I started accepting them. Yeah,
Cool.
so that's very nice.
Very nice. Yeah, well, now it's the time. That is the time for the last word. So, what's the one thing you want the listener to get from our chat today?
I think, like, assuming researchers also listen to that, and not only the DuckDB users. I really recommend DuckDB as for research, because like adding an extension can be very, very powerful, and also like a way to add visibility, or like just have something that's complete, that's usable, because most of the research outputs are artifacts that end up in a shelf, or like are some random Python script nobody can use because you have to install Python 3.10.4 for that, and and I don't have this on my computer. Like if you like maybe, and also like usually like not everything ends up in DuckDB main, so maybe some things can end up in extension, like hopefully the worst case optimal joins at some point, and then it's also fine. And like you can use this to demo things. You can use that to really integrate your algorithms in a system, because it's very different of having it something in like a new hash table layout in a system, because then suddenly you can run TPCH, like a proper benchmark on it, and you can't do that if you're building like your own C program that has struggled reading CSVs. So yeah, there's a lot of infrastructure already there, and it's nice to use it.
Nice. Yeah, it's a good line to end on. Thanks very much, Paul. It's been a great chat. Thanks for coming on the show.
Thank you.